Morning, everyone. So we are getting pretty close to the end of this chapter here. Hopefully you're a little bit more familiar with some of the terminology. So basically, solubility is dissolving the maximum amount. When you hit a point called saturation, we basically have an equilibrium set up. There is leftover undissolved material as a precipitate. The dissolving rate is equal to the reverse rate. We started applying some of those concepts of KSP again. Basically, it's a product between the ion concentrations left over, and especially in yesterday's lesson, even though we had to deal with the mixing question and C1V1, C2V2, we had to do the dilution of concentrations here. Sometimes the concentrations aren't high enough. We can calculate that TIP value, that trial Q value. We basically compare our Q value against KSP. If the Q is actually less than KSP, no precipitate forms. If the Q value is actually larger than KSP, actually a precipitate does form. So in this last little bit here, what I'm going to do is I'm going to just introduce to you two sort of applications to these solubility concepts. So where do we see this in sort of everyday life, and how can I actually take advantage of this? First application I'm going to talk about is referred to as a chloride titration. So let's see if we can just take it apart here, even before I introduce it here. We've seen this word here, titration, before. What's the goal of a titration? Right? Well, the titration here is used to determine the concentration of an unknown substance. And in this case here, the concentration, the titrations that we've done previous are acid-base titrations. We basically run it through a reaction. We basically want to count the number of particles. This is one that's, instead of a neutralization, this is one that's actually going to involve chloride. So let me just hint at how this is going to look like here. We're going to have a solution in the burette. The burette here is the long glass tube. Remember, most of our burettes here are 50 ml burette here. For some reason, the 0 mark is up here. The 50 ml mark is down here. I would generally tell people fill it somewhere more than half. You're going to take an initial burette reading. So initial burette volume. You basically look at the glass chamber and basically state what that number is. Let's say for argument's sake here, it says 10.00. You don't back calculate and say, oh, then that means there's some 40 mils or whatever. You just take that reading. When the reaction is done, when that color change occurs, you know when to stop. Basically, this volume here would now be a little bit less. You're now going to take a final burette reading. And basically, by subtracting these two numbers here, we can end up figuring out how much solution I've actually dispensed in. Remember, you can reload the burette here in between different titrations, but you can't, let's say, oh, I'm keep unloading the solution here. Oh, it hasn't quite changed color. Let me reload. I can't reload in between, or else you're going to introduce a lot of error. Okay, so that's true here. So in this case here, we're actually going to be using, because it involves chloride instead of a acid-base neutralization here, we're going to have some solution with silver in here. Now, I do want to have a like Ag+, but it's in solution. I'm not going to have a chemical bottle of just pure silver plus. So normally what I would do, maybe I have the concentration. I know the molarity of this one, say it's 0.100 molar AgNO3. And again, you might wonder, well, where did the NO3 come from? Again, I know nitrate salts are always soluble. This one here will 100% break up to become a bunch of silver and a bunch of nitrate for me. So I'm going to be dropping in silver here. I'm going to be dropping it into an Erlenmeyer here. The Erlenmeyer here has a nice wide bottom so that I can swirl it around without splashing it up on myself. And basically what we're going to do here is we're going to actually count. In this solution here, it's going to be some unknown amount of chloride. So instead of it being acid and killing off the acid, this time I'm actually going to try to selectively actually count how many moles of chloride. I may not know the concentration. Again, that's going to be in solution. Let's say it's NaCl for argument's sake here. I may not know the molarity. I don't know how many Cl minuses, but what I'm doing here is I'm trying to drop in this Ag+ at a slow enough rate that the Ag+ will slowly kill off the Cl minus, and I basically want to have the point where there's actually no excess left over. I want that last drop of silver here to actually not be able to find the chloride anymore. I would figure out how much solution did I need before that point has happened. That's when the color change occurs, and that's when I know when to stop. How do we do the color change this time? This time we won't use phenolphthalein. Phenolphthalein was nice for us because it turns pink in a base solution. It stays colorless here in an acidic solution here. What we're going to actually use, we're actually going to use a chromate indicator. So chromate here is a CrO4 minus 2. Again, you're never going to have a bottle of just pure CrO4. Maybe I drop it in, let's drop it in as K2 CrO4. Again, oh, where did that K come from? Well, K is an alkali salt, and alkali salt is inevitably going to break up and form the chromate for me. Turns out, in this case here, I'm going to tell you why this ends up working. Turns out we're going to potentially be producing two precipitates. When Ag gets added to chloride, AgCl solid forms. This one here is a white precipitate. So as you do this reaction here, you will steadily be forming a white powder down here, right? So it's not going to be completely clear. It just means that the Ag has found the chloride. It actually solidifies out when the concentrations get to be high enough. What's going to happen here is the second that the chlorides run out, the Ag has no one else to react with. The Ag will then react with the chromate indicator. When it forms Ag2CrO4, this is actually a red precipitate. So we switch over from forming like a white sort of murky material here. Suddenly when it turns to red color, we know we've actually wasted all the chloride, and now I have just reacting with chromate. I just want to verify this with you here. How can I guarantee that the silver actually reacts with chloride first, and when that chloride is gone, only then changes to red color with the chromate? We can actually test it against the KSPs here. So let's just do this on the side here. If AgCl here as a solid, looking at it breaking up, we get Ag plus and we get Cl minus here. Let's do the KSP expression. The KSP is actually silver multiplied by chloride, right? The KSP, I'm going to give you this number here. This number is 1.8 times 10 to the negative 10. Sometimes it is on that KSP table for you. The Ag2CrO4, similarly here, is going to actually break out to become two silvers. So it's not quite a fair playing field here. So I have two silvers and I have a chromate here. The KSP expression there is going to be take the silver concentration and square it, and then multiply it by the chromate concentration. The KSP for that one there is similarly 1.1 times 10 to the negative 12. Now we had done a similar question earlier. We had been saying, okay, yeah, I know this KSP here is some measure of solubility. In general, the lower the KSP means less soluble. I would be tempted to just say, well, the KSP of the silver chromate, this one here is actually less soluble. So if anyone were to actually solidify first, it should be actually the chromate. It should turn red before it actually turns white. But again, like I said, it's a little bit sneaky here. Usually they don't give you a question like this where one of them is a 1-to-1 ratio, the other one is a 2-to-1 ratio. What we actually want to calculate here is, let's calculate. Well, this is the KSP. Yes, no doubt this KSP is actually tinier, but this number may actually be tinier just because of this square here. Let's figure out which one of these solutions will need less silver to actually precipitate. So, just as for argument's sake here, let's find find the amount of silver, Ag plus, needed to precipitate. Let's put in an equal molar amount of chloride and the chromate, because those are the two I want to compare against. Let's, for argument's sake here, to precipitate out, let's say 0.1 molar chloride in the first case, or 0.1 molar chromate. Let's actually verify, maybe it's a squared here that's causing problems here. Let's figure out which one here actually will, in terms of solubility, which one will actually precipitate first. So, again, we can use the KSP. We need to hit this number until we start precipitating. This time, I'm just giving you 0.1 molar chloride or 0.1 molar chromate. Okay, so let's just rearrange it here. I'm interested in finding the amount of silver I would need. I just randomly gave you a 0.1 for the chloride. That could have been any number. And so therefore, the amount of silver that I would need to precipitate out as AgCl first is going to be my first number, 1.8 times 10 to the negative 10 divided by 0.1. Right, so I do that division there. 1.8 e negative 10 divided by 0.1 gives me here 1.8 times 10 to the negative 9. So that's your concentration. What's the silver have to be in the other case here? This time here is a little harder because there's an x squared times it by 0.1, just to play fair. So Ag plus squared is going to equal to 1.1 times 10 to the negative 12. I'm going to divide the 0.1 over as before, but that's just x squared equals that. I'm going to take the root of this to figure out, well, how much silver would I actually need? 1.1 e negative 12 divided by 0.1 with the square root at the end here. The silver would actually need to be 3.3 times 10 to the negative 6 molar before it actually precipitates. So this is a little bit strange. We would normally say the smaller the KSP, the less soluble salt is, but because they're not on a level playing field, the one is a 1-to-1 ratio, the other one is a 2-to-1 ratio, it turned out while this number here were actually tinier, we actually needed more silver before the chromate actually starts precipitating than versus the silver chloride. So in this sort of conclusion here, based on these numbers, based on the solubilities that I found here, the solubility of Ag2CrO4 is actually higher than AgCl, so AgCl precipitates first. And that's sort of misleading here because in terms of KSP, I had expected the smaller the number for KSP here, that one that was actually least soluble. Again, normally in a multiple choice question, they probably play fair. They pick a few compounds, all 1-to-1 ratio. In that situation, if you look at the smallest number for KSP, that one is inevitably going to be the answer. Right? But there we go. We just sort of verify for us here. We had some unknown chloride concentration here. Toss in the indicator right at the beginning, no problem. Because I just confirmed for you that the silver, as long as there's still chloride in this container, the silver will react out the chloride first. Only once the chloride is gone, figure out how much volume that would take, then it's going to then react with the chromate indicator. All right? So this time, although it's not an acid-base titration here, everything else is identical. I'm going to do a question here. Let's say it's AgNO3, that's my solution. That's going to generate the Ag plus ions. I'm going to use them to count how many Cl minus ions that I have. That's going to be the Cl. This is going to end up forming AgCl as a solid. I know naturally it's going to keep creating this white precipitate. I don't need to worry about how much white precipitate forms because the second that my chromate indicator starts reacting, I know all that chloride is gone. That's when to stop. And when you stop it, it then follows a mole ratio. The other counterbalancing ions are just a spectator, Na and NO3. So at the end of the day, it ends up as a stoichiometry problem. Let's just do one of these questions here. Let's say, for argument's sake here, let's say the concentration of silver nitrate I used was 1.2 molar. I did this titration, I took a starting volume, I took a ending volume here, I did the subtraction, and I realized you need to use 34.26 milliliters of the solution before the indicator changed to a red color. So indicator changes to red. And that's when you know when to stop. If it becomes overly red, then you would have an excess, then you would need to start over again. So I have those numbers there fine. I had an unknown molarity of chloride, but even though I don't know the molarity of chloride, it's totally up to me how much volume I want to test at a time. In this case here, how much I want to test here, maybe my pipette here is only 10 milliliters here. Let's say that's needed to react 10 milliliters of NaCl. Even though the setup is complicated, yes, you need to do it slow enough. Yes, you need to be careful not to have any excess and all that. Yeah, you need to find the difference in volume and all that. At the end of the day, this is a standard stoichiometry problem. For all titration questions, even if this were acid-base, only difference here with the equation would be an acid-base neutralization. You're going to take the one that you know more information, the concentration and volume, try to find moles. Why do I care about moles is because I'm at the stoichiometric point here. I now can count how many moles of NaCl unknown that I have, and when joint with the last number here for volume of NaCl, I can then find the concentration of NaCl. So we can actually do that all in one step here. Let's find question mark the concentration of NaCl. Let's start off with the volume. I do want to convert that to liters. So 0.03426. This is liters of my HNO3. For titration, one of the chemicals, you have to know the concentration. So we need to work with that primary standard. I need to dissolve a right amount to make a solution. In this case here, they gave you the concentration is 0.12. Not super precise. I'd like to have more sig figs than that if I could. Based on the mole ratio here, this one here is a 1-to-1 ratio. So for every 1 mole of AgNO3, it's going to be 1 mole of NaCl. Right? I'm just actually interested in the chloride part of it, but the chloride actually would have come from NaCl. And then if I just cancel out those units there, that gives you moles on top. We're going to take the moles and then divide out the 0.0, the initial volume that's in. Remember what ends up happening is we had 10. In this case here, I added an extra 34 from my burette. The total volume would be some 40, almost 50 milliliters. But that's just sort of unfortunate. It's just used to count the chloride particles in the mixture. If I know the chloride particles in the mixture, the chloride moles were actually initially only swimming in. So make sure you use only the initial chloride volume before the titration. I've sort of wasted this sample here. But 0.03426 times 0.12, divide out the 0.01, and this gives me the concentration of chloride to be 0.41 molar. And again, via a stoichiometry problem, via a titration, I've been able to determine an unknown concentration. Now, you'll notice here, the concentrations here were pretty different from each other. The concentration of one of them was only 0.12, the other one was 0.41. Not super crazy. I was still able to carry out one titration via sort of one burette filling. But if I realize that the concentrations were very, very different, I'd either dilute one of them or dilute the other one here. Keep the concentrations close to each other so that you're not running through tons and tons of volume. We usually try to have our titrant to be something more than 10 milliliters so that I can get 4 sig figs, but that's just some experimental details for you. All right? So your questions will have some chloride titrations. At the end of the day, it is just a stoichiometry problem. Right? The one other application I want to do with you today here is something referred to as the common ion effect. This one here brings back a little bit of Le Chatelier kind of work here. So common ion effect, we're going to deal with the ion that is in common in the mixture. And we're actually going to start off, if you've ever visited Alberta, Saskatchewan, some of the prairies here, sometimes you may hear the term thrown around that their water is very hard. So hard water, okay? Well, what does it mean hard, right? Water is a liquid, whatever, right? Hard water is actually the name. Hard water actually contains some minerals inside. Even our tap water will contain minerals, but this one here will typically contain minerals of magnesium and minerals of calcium. It ends up making the water taste a little bit more strange. We really don't appreciate the water being hard. Fortunately for us in Vancouver, our water is really, really soft here. It tastes really good here. We don't have the problem with these ions. Basically, what you would do in places in the prairies here, if you're interested in drinking this water or trying to get rid of some of these ions, you want to precipitate out some of these ions so that you're not actually ingesting these ions. These ions here also some sort of consequences. It makes the water taste weird. In terms of, let's say you take a shower here, right? You're just showering water, but that water there contains these heavy minerals here. It sort of inhibits soap action. So it sort of prevents detergents and soaps from actually being as useful. And sometimes it ends up clogging up drains, things like that. It causes a whole bunch of issues. We want to basically try to solve this issue here. We want to try to remove some of these ions. Yes, if you want to look into detail, you can look into temporary hard water or permanent hard water. I'm not going to get into this. But basically what's happening, imagine we have these magnesium ions and calcium ions. The goal is basically to remove these ions. These are the things that are causing the problems. So what's going to happen here, we have our ions. I have a bunch of calcium in solution. What I want to do is I want to end up precipitating out. A very common chemical that I precipitate out at is, let's precipitate out as calcium carbonate. Let's add something that contains carbonate so that when the calcium ions already in the water, when it runs into the carbonate, it's going to end up precipitating out to form calcium carbonate. So we know this solution here is going to end up in equilibrium. So forward reaction and reverse reaction, dissolving has matched up with recrystallization. But basically, it's going to solve the problem of getting rid of some of the calcium in solution. Now the question is, well, why choose carbonate? Where could I possibly find carbonate here? In fact, our baking soda and baking powder, both of these ones here, one of them is sodium carbonate, one of them is sodium hydrogen carbonate here. It's not that hard to actually get carbonate ions in kitchen chemistry. Now, of course, baking soda and baking powder have their own taste, right? So it's sort of like trading in, well, the water tastes weird and now I have to deal with baking soda water. That's not necessarily a solution for you. But again, chemically speaking, one way of trying to remove this calcium is to add in some carbonate ion. In fact, what we can do here, this is a sort of more generic question, sort of we're using the context of hard water here. What we're actually interested in, let's focus on this equilibrium for a second here. Let's see what we can do. How can we, this is a thought question there, how can we, in this case here, decrease the solubility of CaCO3? Now, why do I ask this question, right? Well, at first, we started with just calcium. Those are the ions I want to get rid of. As you add carbonate, basically what I'm doing is I'm maybe hitting that KSP limit. The trial value is getting high enough so that I'm forcing some of these ions to actually become calcium carbonate. Solubility describes the solid, right? So solubility describes this guy here in going forwards. If I want to maximally get rid of the calcium, I want to shift this equilibrium over to the left side. I want to favor reactants as best I can. what can I do to decrease the solubility? Basically, for the equilibrium that I have, I want the equilibrium to favor or shift to the reactants, right? This is what we refer to as a common ion effect. Well, we've done many different changes. If I knew whether it was endo or exo, this reaction here, I believe it is exo. This is why boiling water helps. When you boil this water, it may look transparent to the eye. When you actually start boiling it, when you increase this heat treatment here, in the presence of carbonate, the calcium ions end up crystallizing out with carbonate and end up forming this chalky sort of white material at the bottom of your kettle. That's actually chunks of calcium carbonate. You can just filter that off. Now that the calcium is gone, now the water is softer. So definitely we can talk about here, let's heat the system. So my stress is going to be by heating, the equilibrium shifts left, removing Ca2 plus as calcium carbonate. That's a precipitate, that's a solid, you would have to filter that off. Is there another way I can do it? This is what more to the point here of why do we call it a common ion effect? Well, because we know that there's actually ions involved, is there a possibility of adding an ion that's in common? So let's say this equilibrium is set up. Let's say at the bottom of my kettle here, we already have chunks of calcium carbonate. Let's sort of keep trying to get rid of the calcium. What can I do to the calcium and carbonate to try to decrease the solubility, to force more of these calcium ions that I don't want in the water, to force them out to actually form a solid? What I can do is I can add something that contains calcium in it. So let's add an ion that's in common. Another thing that you can stress the system out here, let's add calcium nitrate. Or let's add lithium carbonate. And you say, well, wait a second, where did these compounds come from here? I don't really care about what the counterbalancing ion is. It's just that I just want to add calcium. When this one breaks up, this is going to generate more calcium solutions. The nitrate is just going to be a spectator that just sits around. The lithium is an alkali salt. I know it's always soluble. I don't care about the lithium. It's the carbonate that I want. In both of these cases, this is going to up the calcium concentration or the carbonate concentration. That's an ion that's in common in this equation. So I'm going to increase the calcium or increase the carbonate. I know Le Chatelier doesn't like that. It's going to preference the reverse reaction in that case. That's going to shift the equilibrium to the left. That's going to force more calciums to end up powdering out. Yes, you have a fair statement here. Well, I'm not going to have a natural source of calcium nitrate or lithium carbonate, but hypothetically, this would work. By adding ions in common, the equilibrium will shift away from this addition. Just for completeness sake here, this common ion effect here, what if we wanted to do it in reverse? So how can we increase the solubility of calcium carbonate? Not going to be useful for our hard water example because I don't want the ions. I want to get rid of it. Increasing the solubility actually implies more of the calcium carbonate is going to break off. Some of that chalky material is going to then re-dissociate to form calcium ions and carbonate ions. What can I do to actually shift the equilibrium to the right? That's sort of another restatement of this question. How can I make this equilibrium shift right so that I actually end up with more dissolved ions? Well, naturally you'd imagine, well, we can play around with temperature again. Well, if I cool down temperature here, that one definitely pulls it to the right, no problem. It's tempting. Will it work if I add CaCO3? So I have my bottle here that has CaCO3 here. I'm going to add more and more and more of the CaCO3. If you're not careful, you'd be like, oh great, adding CaCO3 increases this, perfect, shifts away from it, perfect. I've increased the solubility, I've made more ions dissolve. The thing you need to be careful of why this doesn't work, adding CO3, there's actually no shift to the equilibrium. The reason, remember, is CaCO3 is actually a solid. Solids have constant concentration. Remember, we did that sort of analogy here. You may have more or less solid. A solid is sort of, well, I have 4 particles in sort of one box of space here. The concentration is like 4. You can add more particle, no problem. So now I have another one of these chunks here. Now I have 8 particles, way more. But it's also taking up twice the amount of room. 8 divided by 2, the concentration still stays as 4. So solids have constant composition. That's why we had ignored them in the KEQ or KSP expression, right? So you can add chunks of calcium carbonate. It just will not affect the concentration of calcium carbonate. This one doesn't go up. It doesn't shift the equilibrium to the right. So that does not work. Now, I don't want you to conclude adding solids never help. I want you to just conclude here, adding the solid in the equilibrium does not help. Adding the solid in the equilibrium does not change the equilibrium, so therefore no shift. What if I added another compound here? So just for argument's sake here, so adding CaCO3 doesn't help. What if I added Na2SO4? I can add that as a solid. You cannot come and just say, oh, solids, constant composition, doesn't affect. Yes, I said the solid in the equation, yeah, adding more chunks of calcium carbonate doesn't shift the equilibrium to the right. That is true. But let's think for a second here. This is a sodium salt, so it's very, very soluble. This is going to break up to become Na plus and SO4 minus 2. How might this equation affect the equilibrium that's involved? Well, earlier we had just plain old calcium and carbonate. They were having trouble forming the solid here. I've now added in the presence of sodium and added in the presence of sulfate. I've added in other combinations you might have solids with. Sodium was fine dissolving with sulfate, no problem. Sodium will perfectly be fine dissolving with carbonate because alkali salts will dissolve with everything. What about calcium and sulfate? When they are in the same solution together, you can check your solubility chart. Calcium and sulfate actually form a low soluble compound, calcium sulfate solid. Right? So in this case here, we have calcium, we have carbonate here. What's going to happen by adding, let me write this in words for you, by adding sulfate, some calcium precipitates out as calcium sulfate, lowering the concentration of calcium. If I'm able to pull a common ion downwards, this one here does change concentration because this one here is aqueous. I'm going to end up shifting the equilibrium to the right. So this one here does work, lowering the calcium to the right and shifting the equilibrium to products and allowing more of my initial solid. Yes, I sort of have to deal with this issue. I just formed another solid. Great, that doesn't really solve my issue. But at least I've allowed the first calcium carbonate solid to dissolve better by pulling down this equilibrium. And essentially, that sort of conclusion there is, if you add an ion in common that ends up precipitating out one of these, it solidifies out one of these, it pulls down the concentration, ends up shifting it to the right. As I shift to the right, more of it dissolves, so therefore the solubility has increased. That's what it means by increasing the solubility of your salt. Now, just before we leave this here, I mentioned here our water in Vancouver here is very, very soft water. So we don't really have to deal with these really hard minerals, magnesium and calcium. We do have minerals. We have some sodium ions, maybe potassium ions in water. That's natural in tap water. That's what deionizing water and distilled water tries to get rid of, but it's good. Some natural minerals are good for us. Our water in Vancouver being very soft, it doesn't clog the drains as easily. It doesn't taste very strange. Our soap lathers really, really easily. A nice application for this here is, let's say when you go buy laundry detergent, the laundry detergent manufacturers, they ship their product to all across Canada. They want to make sure that their product is good, regardless whether your water is soft or regardless whether your water is hard. So what they do is they sort of tweak their recipes so that even in places like Alberta, even noting that the soap is not going to be as good with the hard water, it's going to be good enough to actually wash your clothes. Us in Vancouver, noting that our water is actually so much more soft, we don't need such intense amounts of chemical, such high concentrations, because we don't have to deal with the problems that magnesium and calcium cause. So the application of that there is maybe the manufacturer of your laundry detergent here, they may recommend, oh, you need 2 cups of your detergent. Try it with 1 cup. You're probably going to find that the lathering ability, because our water is actually so soft, you can actually save on detergent with every wash. Obviously, the manufacturers want to sell more product as well, so that's why they always recommend a higher than usual amount. But definitely in the chemistry of this here, because our water is so soft, there's a nice takeaway. If you forget everything in Chem 12, you can use less detergent than they prescribe. Okay, so let me just end off with one last question here. It will deal with this common ion effect, but it's a slightly different way. So, in which solution, I'm going to give you a couple of solutions here. In which solution is SrCO2 most soluble? So I'm going to give you a couple chemicals here. NaNO3, B is Na2SO4, C MgCl2, and D just plain old water. All right. It certainly doesn't look like a common ion effect question. They're not asking, oh, I want to increase solubility, decrease solubility. How can I shift to equilibrium? What they're saying is I'm going to add strontium chloride. I'm assuming equal molar, so just be fair for these chemicals here. In which of these, when I toss it in, will it dissolve the best? Right? Now, thinking about the dissolving reaction, I want strontium chloride to break up to become strontium plus 2 and 2 chloride. We have, as our standard, well, strontium chloride, I always assume that the background was water anyway, so to some extent, as you add SrCO2, you're going to end up getting Sr ions, you're going to end up getting 2 chloride ions for every part that rips up. That's sort of the standard. Is there another chemical that ends up shifting the equilibrium if you want it to actually be more soluble? Let me make a note here. That's sort of our standard. We assume the solvent is water anyways. But is there something that has a common ion? If you want it to be more soluble, you want more of this solid to dissolve. You want the solubility to increase, right? That's going to break up more. It's going to dissolve better, so it's more soluble. So what I want is I actually want to figure out, is there one of these other solutions that has a common ion that in some sense is able to pull the equilibrium to the right? If it pulls the equilibrium to the right, it's even going to dissolve better than water. Let's take a look at our common ions here. So let's take a look at NaNO3. Well, that has ions Na plus and NO3 minus. I don't care if these ones here are solid, although we already said they're solutions. But I have NaNO3, has nothing to do with these ones here. They're not in my equilibrium and they don't precipitate out anything. Alkalis and nitrates are always soluble. Pretty much NaNO3 will be very similar to water, right? No common ions. What if I did MgCl2? How about that? MgCl2 would have Mg ions, will have chloride ions. Chloride is actually in my equation. So if your solution already contains a bunch of Mg, a bunch of chloride here, it's going to be harder for SrCl2 to actually dissolve in because the chloride concentration is already so high. If this is already so high, it's got to shift the equilibrium to the left. So it's actually going to be less soluble in MgCl2. How about sodium sulfate? Our last sort of example here. Sodium sulfate here will have, again, Na ions. It's going to have sulfate ions. Again, I don't see an ion that's in common, but let's do the combinations as well. Na was fine dissolving with sulfate. Is Na fine dissolving with chloride? Yes, alkali salts are always fine. What about strontium and sulfate? In the presence of sulfate, we end up checking the chart. The strontium sulfate actually is going to be a low soluble compound. This one here actually precipitates out as SrSO4. Yes, I end up forming chunks of another precipitate. If my mixture currently is Na2SO4, I start dropping in strontium chloride. That already was solid. I want it to break up. We are going to form extra precipitates of strontium sulfate. But as it pertains to my very starting equilibrium, the equilibrium that I'm interested in, some of the strontium will be tapered off because of the precipitation. That's actually going to cause the strontium chloride to end up dissolving better. So again, let's write that in words here. Since sulfate precipitates some strontium from the initial equilibrium, the SrCO2 is actually most soluble, right? It dissolves the best. We saw that by saying it shifts, equilibrium shifts right if I have equimolar concentrations of the Na2SO4. So it certainly didn't look like a common ion effect. It wasn't like, oh, which one of these can I add to make it more soluble or less soluble? They sort of asked it in reverse. Yes, we have an equilibrium we're interested in. Depending on which common ions I have, maybe I have exactly the ion that I have. This one here is now higher. It's going to be less soluble. In this case here, I added an ion that ends up precipitating out one of the ions, it doesn't matter which. By pulling down the initial equilibrium, I end up shifting the overall equilibrium to the right, and therefore increasing the solubility of your salt. Okay, so that just finishes off chapter 3 for us here. We'll do a summary in tomorrow's lesson and go on from there. Thanks, guys.